right, this is my second attempt to do exponential function video. My first attempt got messed up when my phone said I didn't have enough storage. So here we go. Exponential functions take this form. F of x is equal to a to the y, where a is the base, and a to the y. A to the x, a is the base, and x is the exponent. So how you recognize an exponential function is the variable x appears in the exponent, and so that is an exponential function. Sometimes people get it confused with things like this, y equals to x cubed, or y equals to x to the 7th, or something like this. These are not exponential functions. These are polynomials. These are power functions. The variable does not appear in the exponent right here, so these are not exponential functions. So the rules with definition of an exponential function is that the base a cannot be 1, because 1 to anything is just 1. That would just be a boring horizontal line. That's not an exponential function. And that the base a is positive. How they handle negatives, if you have a negative, you handle that like a reflection across the x-axis. So the base is positive, and it can't be 1. All right. So this kind of splits into two categories. One is where the base is, I did this last time, the base is greater than 1, and the other is where the base is between 0 and 1. Okay, so first let's look at this case, where the base, being raised to a power, is bigger than 1, and so I wanted to choose something that we're familiar with, so I chose the base to be 2. This will serve fine because 2 is bigger than 1. So we're going to look at 2 to the x power. So what we should do, on your sheet I kind of gave us a way we could point plot. So if we've got x and we've got 2 to the x right here, I'm going to choose some values for us to put into our domain here. Maybe when x is -2, -1, 0, or 1, or 2. Let's see what our output for these would be. 2 raised to the -2 power is 1/4 is what that would be. 2 to the -1 power is 1/2. 2 to the 0 is 1, because anything raised to the 0 power is 1. 2 to the 1 is 2. 2 to the 2 is 4. What this gives us is a few points. -2, 1/4. -1, 1/2. 0, 1, 1, 2, and 2, 4. When x is 2, y is 4, and so on. So let's plot these. Over here at -2, at x is -2, we're only up here at 1/4. And when x is -1, we're up at 1/2. And when x is 0, we're up here at 1. And when x is 1, we're up here at 2. And when x is 2, we're up here at 4. All right, so we get these points, and we can just fill in the curve. It hugs the x-axis, and then it begins to increase like this. This is what an exponential function looks like when the base is bigger than 1. You may have seen this, unfortunately, on the news recently about the coronavirus. There are many people catching it, and it's spreading at an exponential rate. And so you might have seen this curve. Hopefully it will quit being exponential soon and level off. But anyway, there are many applications for exponential functions. You can plot population growth, or bacterial growth, or traffic patterns. There's all kinds of things that you can plot with exponential growth. Also exponential decay, when something's getting smaller, that's something else we'll be looking at as well. The second category is when the base is between 0 and 1. What does this curve look like? Let's just plot that. I chose, for these purposes, the base would be 1/2. 1/2 is a number that's not too strange to us, and it would serve our purposes here because it's between 0 and 1. So here's some x values we can put in here, and we'll say 1/2 to the x. So let's do the same ones. -2, -1, 0, 1, and 2. Let's have a look at what happens. When 1/2 is raised to the -2 power, this is 1 to the -2 over 2 to the -2, or 1, I'm sorry, you can cross the fraction bar to make them positive. So this is 2 to the +2 over 1 to the +2, or just a 4. All that to say that at -2, the y value is 4. 1/2 to the -1 ends up being +2. When x is -1, y is 2. 1/2 to the 0 power is 1. When x is 0, y is 1. 1/2 to the first power is 1/2. When x is 1, y is 1/2. 1/2 to the second power is 1/4. When x is 2, y is 1/4. So we can plot these values over here. When x is -2, we're up here at 1, 2, 3, 4. We're all the way up here at 4. When x is at -1, we're up here at 2. When x is 0, we're at 1. When x is 1, we're at 1/2. When x is 2, we're down here at 1/4. So these are the points that we get for this particular graph, and we can connect the dots. And this is what it looks like. So these look similar. They're a reflection about the y is what they are. What is the difference in these two functions? Well, this one is very close to 0, and as it increases very quickly. It is an increasing function. Over here, towards the left side, it's very, very high, and as x increases, it gets smaller and smaller and smaller and goes almost to 0. It goes almost to 0, but so in both of these cases, what we have is it getting very, very close to the x-intercept, and this is a horizontal asymptote called y equals to 0 is a horizontal asymptote. And so here's some things that we can fill in. Is there an asymptote for either one of these graphs? And it is the same for both of these. There is an asymptote at y equals to 0, a horizontal asymptote. Let's see, what is the domain of this function over here? How far to the left and how far to the right would it go? Well, you can put any real number you want into this. The domain is -infinity to +infinity. If we look at this graph, the domain is also -infinity to +infinity. How about the range? Well, the range is as close as we can get to 0 to infinity over here. What about over here? The range is as close as we can get to 0 to infinity. The range is the same for both of these functions as well. Is there an intercept? There is, and it's the same intercept. They're both a y-intercept at 0, 1 here, at 0, 1 here. Why is that? That's because when you raise anything to the 0 power, it equals to 1. Anything to the 0 power, it equals to 1. So you will always have that intercept. What could we say about these functions? Does this function pass the horizontal line test? Or you could say, is it 1 to 1? Or you could say, does an inverse exist? Those are kind of all asking the same things, and the answer is yes. So we could say that this function, as well as this function, is 1 to 1. It passes the horizontal line test. An inverse exists. So what is the big difference here? Here's the big difference. This function, when the base is greater than 1, is increasing. This function, when the base is between 0 and 1, is a decreasing function. What are some other functions that would look almost exactly like this and would have all of these same statements to be true about them? What if we had this? F of x was equal to, how about 3 to the x? 3 is bigger than 1. Yes. How about f of x is equal to e to the x? E is a number. It's 2.7 something, bigger than 1. Yes, it would look like that. How about f of x is 1.2 to the x, bigger than 1? It's going to basically look like that, and all of these same things can be said about it. What about here? Can we pick some other ones that would take on this same basic shape? Sure, just pick a base that's between 0 and 1. How about f of x is equal to 2/3 to the x? Yes, that would do. F of x is equal to 1/4 to the x. Yep, how about f of x is equal to 0.398 to the x? Yes, all of these bases are between 0 and 1, so all of these same things would be said about them, and it would take on that shape. Okay, very good. Let us move on down the sheet. Next, we have some calculator practice. Get your calculator out. And so what we're going to do is just practice pressing a couple of buttons. I'm going to do 2 of these, and you can do the other ones. How about if I say, let's evaluate E. raised to the 5 raised to the 1.7 to 3 decimal places, all right? You're going to say 5, and then to raise it to the button, you hit the caret button, the rooftop button, raise to the 1.7, hit enter, and I get 15.4258, 15.4258. So if I need to round to the 3rd decimal place, I look next door, it's a big 8, this will turn into 15.426 is what that will round to. What about the next one? How about e to the negative 1.3? E to the negative 1.3. Well, there's 2 places you can find your E button. One is above the division sign, and the other's above the LN button, and they're both in blue. So to get to those, you have to press the second feature. So hit second, and I'm going to hit the LN, and what that does is say E to the power. So if your calculator already puts it up in a superscript power, that's great. And if it doesn't, it'll do a caret and a parentheses, and you just fill in the power and close the parentheses. Remember when you're leading with a negative to press the negative in the parentheses, negative 1.3, and I get 0.2725, 0.2725. This is the 3rd decimal place. I look next door, it's a 5. Let's round this guy up to a 3. I think you guys can do the other ones on your own. Let me go ahead and do the atmospheric pressure. I'll do one of these. So on your worksheet, it says the atmospheric pressure P on a balloon or plane decreases with increasing height. This pressure, measured in millimeters of mercury, is related to the height h in kilometers above sea level by the function P of h is equal to this. So here's the function. P of h is equal to all of this. 760 e to the negative 0.165 h. Okay, there we go. And it says find the atmospheric pressure at height of 2 kilometers and at a height of 10 kilometers. So I'm going to do the one for 2 kilometers, and you're going to do the one by yourself for 10 kilometers. So h represents the height in kilometers or kilometers. P represents the pressure at a height of h in millimeters of mercury, millimeters, and this is the symbol on the periodic table for mercury, or you could just write the word mercury. So what we're asked to do is find the pressure when the height is 2 kilometers and also 10. So to find it when it's 2, I'm just going to substitute the number 2 in for h. 760 times e to the negative 0.165 times 2. I'm going to use my calculator now, and I'm going to say 760. I'm going to hit my second LN button, which gives me the e raised to a power. I'm going to say negative 0.165 times 2, and I get 546.4, if I round it to the 10th place, millimeters mercury is the pressure. P of 2 is equal to this. All right, now lastly on your sheet, we have the compound interest equation. So let's look at that, compound interest. Compounding interest is where you earn money on your money, or where you pay money on the money that you borrowed, basically. So let's just say I borrowed $1,000 from the bank to buy something. They will charge me a certain interest rate, and so I have to pay interest on the money that I borrowed. But with compound interest, they stop so many times per year. They say stop. Let's say they're going to stop 6 times per year. They stop, and they're like, okay, let's stop and add on how much interest you already owe us. Let's add that to the amount of money you're drawing interest on. And so instead of paying interest on $1,000, you pay interest on $1,000 plus that little bit they added on. So it's higher interest rate, really higher interest that you're going to pay. Then they stop at the second stop, and then they say stop. Okay, stop. How much more interest have you gained? Let's take that little bit of money and add that onto the amount of money you're drawing interest on. So you end up paying extra money on the money you borrow. Now it works in reverse. If it's a savings account or an investment account, you earn money on the money that you lent someone to invest. So if you give somebody $2,000, a bank, and say, okay, I want to draw interest on my savings account, but I want it compounded monthly. Every month they will stop and say, well, how much interest has this gained? Let's add that to the amount of money that you're drawing interest on. And so then you would not just get money on interest on the 2,000, but the 2,000 plus the whatever. Stop after another month, add that little bit on. You draw money on that. So it works better for you if you're the one who's investing, worse for you if you're the one who borrowed. So more compoundings per year. So this is the letter, the variable n is what we use, and it means the number of compoundings per year. So what's important is to be able to read the problem and understand what kind of compound interest is going on. So if they say something is compounded daily, or monthly, or yearly, or semi-annually, or what else would they, weekly, or daily. When you read this word, something's compounded, oh, I already did daily. Something's compounded this often, that is telling you that there is a variable called n in here, and n is equal to this many times per year. Oh, quarterly. I think that's the one I wanted to put on there. Quarterly. Okay, so what would daily mean? The convention that we go with, even though this isn't exact, is that there are 365 days in a year. So in this case, n would be 365. How many months? 12. This is going to stop 12 times a year and draw more interest. If they do it yearly, then it's going to be once a year. Semi-annually, that means twice a year. N would equal to 2. Weekly, that means they're going to stop 52 times. There's 52 weeks in a year. Quarterly, they're going to stop 4 times a year. So that is how you can decide what N equals to. Now let's look at the formula for compound interest. The formula for compound interest goes like this. A of t stands for the amount in the account at any time t, and in this case t is in years, is equal to P, which is the initial amount of money that you invest called principal, times 1 plus the interest rate R divided by N, the number of compoundings per year, times N, the number of compoundings per year, times T, how long it's been invested for. So on your worksheet, I have that formula right there. And if you look at the bottom of the worksheet, it has all of these things I just said what they were. It has their description right there. So what I'm going to do is just pick a couple of these, the ones on the chart for us to fill in. Let's do number 56, and then let's do number 61. Let's do 56, 56, and 61, and you'll see how these go. 56, they say that the principal is equal to $12,500. 12,000, oops, that's a $12,500, okay. And then it says that the interest rate is 3%. So 3%, but we always calculate in decimal, 0.03. It says it's compounded quarterly, so N is 4. And it's going to be invested for 3 years, so T is 3, and they want us to figure out what A is. What is A of 3 would equal to $12,500 times 1 plus 0.03 divided by 4, which is N, raised to the 4 times 3, which is T. And we'll put this in our calculator. We will round to 2 places because it's money. So real quickly, on your calculator, you can say, I always start order of operations. I start with the innermost parentheses. And so I'm going to start with 0.03 divided by 4, and I hit enter. Then I say +1 and I hit enter, and every time I hit enter it calculates it to one value. Now I have 1.0075 in my calculator. I'm going to raise that. I'm going to use the rooftop and raise it to 4 times 3. So I'm going to raise it to the power of 4 times 3 and hit enter. And now I have 1.0938 and some more digits. So all of this part is done. I'm simply going to multiply that times 12,500, and that gives me that the amount in the account after 3 years is $13,672.59. So 61 goes like this. Number 61 says our principal is $17,400, and let me just, don't be fooled. You will never find, I don't think, an interest rate of 8.1%, but if you do, congratulations. 61, the principal is, let's see, $17,400. Okay, cool. Then it says that the rate is 8.1%, which I have never seen, but this is 0.081. It's daily. Wow. Okay, so this is going to stop and get compounded 365 times per year, and this is going to go on for 5 years. T is 5. What is the amount in the account after 5 years? Okay, it's equal to P, 17,400, times 1 plus R, 0.081, divided by N, which is 365, raised to the 365 times 5, which is the amount of time. In my calculator, I'm going to start with the order of operations. I'm going to say 0.081 divided by 365, and I hit enter. Plus 1, I hit enter. I'm going to raise it to this power, raise to the 365 times 5 power, and I get 1.499235 and some more digits. Now I'm just going to multiply that number times 17,400, and I get 26086 and 69 cents. This is the amount in the account after 5 years.